Okay, so today we're going to study what is Doppler effect. So Doppler effect is defined as the apparent change in the frequency caused by the relative motion between the source of the wave. So in this case, this is the source of the wave, and the observer. So basically what happens is, take a common example. So take an example of a fire engine. So you would have observed that when a fire engine comes closer to you or is coming towards you, then the sound of the siren gets high pitched, and when it goes away from you, the sound of the siren becomes low pitched. So this is a basic example, and this is exactly what is Doppler effect and how Doppler effects come into effect when the source, the sound making source, or um, the source of the wave comes closer to the observer or goes away from the observer. So again, what was Doppler effect? Doppler effect was basically apparent change in the frequency caused by the relative motion between the source. So relative motion between the source and the observer. So now we would go into a basic depth. So what is how Doppler effect works and how you hear a high pitched sound and a low pitched sound. So take an example of this scenario where this point, like which is marked in green color, is the source in both the cases. So yeah, so this is the sound emitting source or any wave emitting source, and here are two observers, observer A and observer B. Okay, so you would agree that the wavelength is the same in like between two successive waves, the wavelength remains the same in both the cases. So either it's this or it's this or it's this. So wavelength remains the same. And then there are again two observers, observer A and observer B, right? So you would agree that, keeping in mind that velocity is constant, that is basically the wave velocity or the velocity of the wave, so that is constant. So v equals to f lambda. If lambda is constant, then frequency would be constant. So the frequency at which the observer A hears the sound is same as the frequency of the sound heard by observer B. However, in this scenario, the second case, this is the first case and this is the second case. So in the second case, when object starts to move towards the right, what will happen? Like, take an example of the fire engine. So it is now moving towards observer B and going away from observer A. So taking that example of fire engine, if the fire engine goes towards the observer B, then it would hear a high pitched siren, and observer A would hear a low pitched siren. So what basically happens? Why do two different observers positioned at different places hear different frequencies of wave, differently pitched sounds, even though the sound is coming from the same source, but the source is moving? So the reason is, take an example of this specific scenario where the object is moving and the waves that are produced. Now, what is happening? That the object, since it is moving towards the right, what will happen that, like, let's say that there is bending. So if it is like this, then if it moves towards the right, then this object and this, and if you would compare the size of this circle and this circle, or you could say this wave with this wave, you would see that they both are equal. And the only thing that has changed is the distance between the source from one point of wave and the other point of the wave, for the first wave, for the second wave, and so on and so forth for the third and the fourth and the fifth wave. The reason why this happens, that is the change. And again, since there is a difference in distances, that is the reason why you could see clearly The wavelength between these, between the wave and the other wave, the first wave and the second wave, is not equal to the wavelength from this point of one wave to this point of the second wave. And this tells us that wavelength here is shorter, and since velocity is constant, so a shorter wavelength corresponds to a greater frequency. And here the wavelength is greater, so velocity being constant, a greater wavelength would result in a lower frequency. So this is proven, right? But why does this happen? Why these wavelengths get changed? And the reason is pretty simple. So you just have to imagine, like, take an example of a source and a wave. So what would happen if this source moved towards the right? The rate at which my waves are produced would remain the same. However, due to the movement of my source, what would happen that my source moves towards the right and becomes more closer to this part of its wave than this part. Since it's moving away from this part and going closer towards this part, that's the reason why the distance between two successive waves in this part of the waveform and this part of the waveform is different. And due to the changes in the wavelength, if wavelength increases for a constant velocity, frequency decreases. If wavelength decreases for a constant velocity, frequency increases. And this is it. This is basically the concept of Doppler effect. And now we will just look what is the formula of observed frequency in Doppler effect. So basically there are two formulas. Both are the same, just the difference lies in the sign of the denominator. So whether it's going to be added or it's going to be subtracted, so that's only the difference. So the general formula of Doppler effect is frequency observed is equals to the frequency of the source times the velocity divided by velocity, and this v and this v basically represent the same velocity, that is basically the velocity of wave. So whether it's a light wave or a sound wave, so yeah, then plus minus velocity of source. So if we just break these two plus and minus into separate equations, so it becomes frequency of frequency that is observed is equals to frequency of the source times velocity divided by velocity plus velocity of sound, or the other equation becomes observed frequency is equals to frequency of source times velocity divided by velocity minus velocity of source. So the question is why there is just a difference of a plus sign and a minus sign. So let's take some um random values. And okay, one thing that you could easily observe that the numerator in this fraction is equal to the numerator in this fraction. The difference lies only in the denominator, and that is a difference in signs. So let's take some random values. Let's say the frequency of the source is 3 hertz. The velocity of wave is 10 meter per second. Just random values. Again, 10 meter per second, and the velocity at which the source is moving is 2 meters per second. Okay, what we learned before in this specific part, we knew that when objects go towards, that is basically when the source go towards the observer, frequency increases because pitch increases, and when sources go away from the observer, the frequency decreases as the pitch decreases. Okay, so we would apply this formula, the first one and then the second one. So first one, frequency of source was 3 hertz, velocity of the wave is 10 divided by the velocity of wave was 10 plus the velocity of source was 12. So the answer is 30 divided by 12. hertz because it would be the frequency of observer. Okay, and then for the second part, frequency of observer would be frequency of source, that is 3 hertz, times velocity, that is 10, divided by 10 minus the velocity of the source, that is 2. So the frequency of observer becomes 30 divided by 8. You could clearly see that this value is greater than this value. So what does this imply? How do we know that which formula is for which specific scenario? So again, what we learned was that when source moves towards the observer, frequency increases. When source moves away from the observer, frequency decreases. So what has happened? 30 upon 12 is equals to 2.5 Hertz, and 30 upon 8 is equals to 3.75 Hertz. What has clearly happened? The original frequency was 3 Hertz. Now this frequency is 2.5 Hertz and this frequency is 3.75, means that this frequency has increased and this frequency has decreased. So you could easily deduce that this means this specific value tells us that as my frequency has increased, this means that my object that emits my waves, or that we could say the source, move towards the observer. And this specific scenario tells us as my frequency is decreasing, the source moves away from my observer. And this makes it easier to understand which formula is to be used in which scenario. So when sources go away from my observer, the best formula to use is frequency of observer is equals to frequency of source times velocity divided by velocity plus velocity of my source. And when sources go towards the observer, the formula to use is frequency of observer equals to frequency of source times velocity divided by velocity minus velocity of my source. And we could easily see that since here the denominator would be greater, so the value would be lesser, and here the denominator would be lesser, so the value would be greater. And this makes it easier to understand and to remember that this formula is used for this specific scenario, and this formula is used for this scenario. And so we are done with Doppler effect.